Okay, let's take a look at the American Invitational Mathematics Examination from the year 2022, test number 2, problem number 8. And the problem states, find the number of positive integers n. Less than or equal to 600, whose value can be uniquely determined. When you know the values of the floor of n over 4, the floor of n over 5, and the floor of n over 6. So first I want to restate this problem just to make sure that I'm understanding it correctly. And I'm going to say let there be a set S of integers n, positive integers n, such that n is less than or equal to 600 and some property u of n holds. And this is going to be the property that n is uniquely determined by those three floor values. So how am I going to express u of n? I'm going to say for all m in the integers, m is equal to n, or f of m does not equal f of n, where f is just a triple of these floors. Floor n over 4, floor n over 5, floor n over 6. And then the problem will be to find the number of elements in S. Great, so first I just find myself more comfortable when I've written it out like this. And I'm actually not sure if this should be z plus here or just z. Is this asking for, when it says n is uniquely determined, does that mean any other integer n will have different floors, or does it mean any other positive integer n will have different floors? If you think there should be a plus here, then there's a little corner case that you have to worry about later, but it doesn't change the final answer. So for simplicity, I'm just going to assume there's no plus here. Alright, so with that out of the way, let's start by considering there are these intervals of equal length, and everything inside an interval will have the same integer part when divided by 4, for example, if 4 is the length of the interval. So maybe there's 0, 1, 2, and 3 in this interval, 4, 5, 6, 7 in this interval, and so on. That means everything in this interval will have an integer part 0 when divided by 4, and everything in this interval will go to 1, and so on. You'll have 2, 3, they'll just keep increasing. And if we have some number n, and it's at the left end of one of these intervals, then you can't move it any farther left without changing the value of f of n. And if it's at the right of one of these intervals, then you can't move it any farther right without changing the value of f of n, because it will enter a new interval. What else? Let's also consider the case where, let's say n is here. It's at the right end of this interval, but it's not at the left end of any interval. So it's free to move to the left without changing the value of f of n. So I think this is the same as our uniqueness property u of n. So let's just write out, how can we express this property of being at the left of an interval and the right of an interval? I'm going to call this P of n, and we can say this is n congruent to 0 mod 4 or n congruent to 0 mod 5 or n congruent to 0 mod 6. That will tell us that it's at the left side of some interval. And we also want it to be congruent to -1 mod 4 or to -1 mod 5 or to -1 mod 6. And that will give us that it's at the right of an interval. And I've already sort of convinced myself that P of n is equivalent to U of n, but let's show that in a little bit more detail. And we're going to start by considering the case when n is congruent to 0 mod 4. For all m less than n, we can say that the floor of m over 4 is less than or equal to m over 4. That's because the floor of a number is always less than or equal to that number. And this m over 4 is less than n over 4 by our assumption here. And n is congruent to 0 mod 4, so this equals the floor of n over 4. And this is telling us that f of m, its first coordinate anyways, is equal to f of n in its first coordinate. I'm sorry, it's telling us that they're not equal because we have a less than here. And since they differ in their first coordinate, that means the point overall differs. So we can conclude f of m does not equal f of n. Now, likewise, if n is congruent to 0 mod 5, by a similar argument, we can conclude f of m does not equal f of n for all m less than n. And we can make the same conclusion if n is congruent to 0 mod 6. So altogether, if we have n congruent to 0 mod 4 or to 0 mod 5 or to 0 mod 6, we can conclude f of m does not equal f of n for all m less than n. Now let's look at the case n congruent to -1 mod 4. Then for all m greater than n, the floor of n over 4 is less than or equal to n over 4, which is certainly less than n plus 1 over 4. And n plus 1 is divisible by 4, so this equals the floor of n plus 1 over 4. And if m is greater than n, that also means m is greater than or equal to n plus 1, since m and n are integers. And since the floor is an increasing function, this is less than or equal to the floor of m over 4. So we've shown that f of m in its first coordinate differs from f of n in its first coordinate, and since they differ in one coordinate, the points differ. Great, and again, just like before, we have or n congruent to -1 mod 5. We can come to the same conclusion by a similar argument, and if n is congruent to -1 mod 6, same conclusion again. So overall, this implies for all m greater than n, f of m does not equal f of n. So P of n will imply this formula 1 and this formula 2. So if 1 and 2 are both true, we can say for all integers m, m will either be equal to n or it will be greater than or less than. But in either of those two cases, we've shown f of m does not equal f of n. And this is exactly u of n, right? Let me just check. Yep. So we've shown more formally that p of n implies u of n. Let's get rid of this to make some space. And if you're in the test environment, I don't know if you'll have time to go through all this. You might have to wing it a little bit. Just kind of satisfy yourself with this diagram here. But since I thought about the details, I figured I might as well share them with you. So now we want to prove not p of n implies not u of n. So let's take a look at what not p of n is. All of these will be negated, and then all of these ors will turn into ands. And that and will turn into an or. So let's first look at the case n not congruent to 0 mod 4. Well, the division theorem, I think it's called, tells us that there exists a q in the integers and an r in the set 0, 1, 2, 3, but we're excluding 0 here, so we just have 1, 2, and 3, such that n equals 4q plus r. And now the floor of n over 4 will be the floor of 4q plus r over 4, which will be the floor of q plus r over 4. And since q is an integer, we can pull it out of this floor function and get q plus the floor of r over 4. And r over 4 will be either 1/4, 2/4, or 3/4. In any case, its floor is 0, so this equals q. And now let's look at the floor of n minus 1 over 4. This equals the floor of 4q plus r minus 1 over 4. And this equals q plus the floor of r minus 1 over 4. And r minus 1 over 4 will be 0, 1/4, or 2/4. And in any case, its floor will be 0, so this equals q. And from these two expressions, we can conclude that f of n in its first coordinate equals f of n minus 1 in its first coordinate. And by a similar argument, if we have n not congruent to 0 mod 5, we can say that the second coordinate is the same. And if n is not congruent to 0 mod 6, then its third coordinate is the same. So since all the coordinates are the same, we know f of n equals f of n minus 1. Great, now let's consider n not congruent to -1 mod 4. The division theorem tells us that there exists a q in the integers and an r in the set 0, 1, 2, 3, but we're excluding 3, so we have 0, 1, and 2, such that n equals 4q plus r. Then the floor of n over 4 is going to equal, I'm going to skip some steps here and just say it equals q plus the floor of r over 4. R over 4 is 0, 1/4, or 2/4, so this equals q. And now let's look at n plus 1 over 4. Not n minus 1 like we did before, but n plus 1. This will equal q plus the floor of r plus 1 over 4. R plus 1 over 4 is 1/4, 2/4, or 3/4, so this equals q. And we've shown that f of n in its first coordinate equals f of n plus 1 in its first coordinate. And if you have n not congruent to -1 mod 5, you get the second coordinates being equal. And if n is not congruent to -1 mod 6, their third coordinates are equal, and so together we get f of n equals f of n plus 1. Great, and I'm just going to call this statement 1 and this one 2. So Not P of n is telling you that either 1 is true or 2 is true. But from 1 or 2, we can draw the same conclusion, that being there exists an m in the integers different from n. In case 1, we're going to let m equal n minus 1, and in case 2, m will be n plus 1. But in either case, there is an m different from n with f of m equals f of n. And this is exactly the negation of u of n. So we should be happy because we've shown the other direction of this implication now. And this is where that corner case I talked about comes into play, because if we think there should be a plus here, then what we really want to show is there exists an m and z plus with this condition. And that's a problem in case 1, because what if n equals 1? Then this is telling you that f of 1 equals f of 0, which is nice, but 0 is not an element of z plus, so we cannot conclude that there's an m in z plus with this property. But if you give it a moment of extra thought, you'll find that it's not really a problem. I'll just leave that as an exercise to the viewer, I think. So let's get our p of n back here. So all these ands will turn back into ors. All those negations go away, and you get an and here. So yeah, we've shown p of n equivalent to u of n, which is nice because p of n is a lot easier to work with, I think. And now we can rewrite S as the set of all n in the positive integers, such that n is less than or equal to 600 with the property p of n holding true. And now I just want to distribute all the terms in p of n. So I'll start by considering these two terms. If n is congruent to 0 mod 4 and n is congruent to negative 1 mod 4, that will have no solutions. There's no n satisfying those two conditions. Next, we'll look at these two. If n is congruent to 0 mod 4 and n is congruent to negative 1 mod 5, since 5 and 4 are coprime, the Chinese remainder theorem tells us that there will be one unique solution modulo 20, 20 being 5 times 4. So we can say n is congruent modulo 20 to some number, and if we think about it for a second, 4 works. 4 is a multiple of 4, and 4 is 1 less than 5, which is a multiple of 5. Continuing on with our distribution of these terms, we have n is congruent to 0 mod 4 and n is congruent to negative 1 mod 6, but if it's congruent to 0 mod 4 then it's even, and if it's congruent to negative 1 mod 6 then it's odd, and we can't have a number being even and odd, so there's no solutions there. Next, let's look at n congruent to 0 mod 5 and n congruent to negative 1 mod 4. Again, we can use the Chinese remainder theorem to say that n is congruent mod 20 to some number. And if we think about it for a second, 15 works. 15 is a multiple of 5 and it's 1 less than 16, which is a multiple of 4. Next we have n congruent to 0 mod 5 and n congruent to negative 1 mod 5. No solutions there. Next we have n congruent to 0 mod 5 and n congruent to negative 1 mod 6. Again, 6 and 5 are coprime, so the Chinese remainder theorem tells us n is congruent mod 30 now to some number, and that number will be 5. Okay, next. Which one is next? I think it's this one, n congruent to 0 mod 6 and n congruent to negative 1 mod 4. And again, we have an issue with oddness and evenness, so no solutions there. Next we have these two, and we'll get one solution mod 30, and that will be 24. 24 is a multiple of 6, and 25 is a multiple of 5. And finally, we have these two. There's no solutions there. So P of n, after being expanded, is equivalent to this expression. And we can take a look at n mod 60. It will have to be one of the following numbers. I want to look at n mod 60 because 60 is the least common multiple of 20 and 30. So if n is congruent to 4 mod 20, it can be 4, it can be 24, it can be 44, and then after that the solutions will go above 60 and they'll start repeating. So we only have to write down these three. If n is congruent to 15 mod 20, we get 15, we get 35, and we get 55. If n is congruent to 5 mod 30, we get 5, and we get 35, but we already have that in this set, so we don't need to write it again. And you might not want to write it again because it might screw you up in the next step. Anyways, if n is congruent to 24 mod 30, we get n can be 24, which we already have, or it can be 54. So we have 8 solutions in the interval 0 to 60, including 0 and not including 60. But we can just change that to not include 0 and to include 60 because neither 0 nor 60 are solutions. And then we know that P of n is periodic. P of n equals P of n plus 60 for any n. So we can just splice together a bunch of these intervals, and those 8 solutions will just repeat themselves in each copy of the interval. So if we splice together 10 copies of this interval, we'll get the interval from 0 to 600. And since there are 10 copies of those, we have 10 times as many solutions. 80 solutions in this interval. And this is the interval that we are concerned with here. So 80 is our final solution. Great, thanks so much for watching.